talk. So it's my great pleasure to welcome Teresa Vidal Calleja, who's going to meet us. He's coming from UTS just down the road, so a lot of people probably have met Teresa before. Teresa's currently Associate Professor and Deputy Head of School for Education, I think
research.
The other way around, at the Department of Mechatronics Engineering at UTS. And Teresa studied mechanical engineering, electrical engineering, bachelor's and master's in Mexico, and then in Polytechnic University of Catalonia for the PhD, and did postdoctoral research here at ACFR at some point, I think, for a while, and then moved to UTS in 2012. Is that right? And I guess you're currently researching in manufacturing, meat and livestock, mining, medical devices sector in the robotics kind of autonomous area.
Yes.
I think we first met, I guess, probably when you were here, probably about 2006, when during your PhD.
During my PhD.
Yeah, so Teresa's been around at the ACFR for quite a long time, I guess, not longer than a lot of people see.
Yes, correct.
Right. Thank you very much.
Yeah, thanks, Mitch. Thanks for the intro. Being here is like putting the time backwards, right? It feels the same. Actually, it looks the same too. But yeah, it's great to be here again and giving you a talk of what I've been doing in the past few years only. But yeah, it's good to see very well-known faces. So as the title says, I'm going to talk about our work on continuous models for sensor integration, localization, mapping, and planning. It says planning, but I won't show anything about planning. Anyway, the representations are suitable for planning. But yeah, so just as a quick, as well, Mitch already introduced it. This slide just for people who don't know. Well, yes, I'm in UTS now. I did my PhD in Barcelona and then a postdoc in LAAS in France, and then another one in ACFR, and then moved to UTS. So the outline of my talk is I'm going to talk about a very brief introduction of the Robotics Institute at UTS, and then I'll move on to a more technical talk that it's split into two, almost four, but hopefully it's not too crazy and I have enough time. So the Institute. So you might not know, despite we are across the road, that we changed names just recently. So it used to be the UTS Center for Autonomous Systems, but right before COVID, the university wanted to kind of bring under the same umbrella all the robotics research in UTS, and we created the UTS Robotics Institute. So for now, we have around 70 people, plus minus, with 10 academic staff, around 10 postdocs, and then like 50 students. We do research in sensing, perception, that's more estimation, that's my area, but there's a lot of people working on human-robot interaction, control, planning, coordination, and general robotic systems, like building actual robots. And we teach an undergrad program in mechatronics, which has lots of students with 500, well, I don't know how many you have in here, but feels like a lot sometimes. So just a few highlight projects, and don't get scared, I'm not going to show all these videos because it's we have lots of these kind of marketing videos from UTS, and they take like 3 minutes or 5 minutes each, but I'm not going to go through all, just few highlights. So in the past, I guess, 10 years, UTS has been very good at engaging with infrastructure maintenance industry. We have lots of projects in with Sydney Water for water, our water utilities like drinking water and wastewater as well, like sewers. So there has been, we have robots today that are actually deployed in our water pipe network. And lots of projects keep coming. I guess there are many needs, a lot of data analytics as well. We have an Institute of Data Science that collaborating with the Robotics Institute. We're helping Sydney Water in many ways. So this is just some, the first one, and I'll show it on, I was asking for a laser pointer, but I thought obviously for the, no, it's, I don't need it because I realized we're doing hybrid. So we actually need, I need to point out with my arrow anyway. So yeah, we have, this is a project on water pipes, and this is a project for sewers. Anyway, like we have robots, deployed robots inside pipes and sewers. Right, so I'm just gonna stop these two and go to this one. So another big area where UTS has been working on is the infrastructure maintenance as well for bridges. Like we have a big research with engagement with RMS, Road and Maritime Services of New South Wales. So there are robots operating in the Sydney Harbour Bridge that goes inside and inspect, try to clean it. So this is just the one show here is just the first generation. Now we have only the second generation. But yeah, like the second generation is actually cleaning. This was just inspecting. And yeah, like, but biologically inspire all this. Other work that we have that has been very successful in UTS. We had a collaboration through the CRC rail manufacturing to do monitor passenger behavior in train stations. So we put together a system that it's able to count and track people in. I'm just gonna fast forward this because it's mostly the student talking, but monitors behavior of people in train stations. Yeah, we counted them. It's just a simple camera, 3D camera system to avoid, having to have images. We just use point clouds and then track people around. And another kind of line of working is in collaboration with manipulators. Collaboration with robots to help workers, right? So co-working with robots, like imagine for doing very, how do we call it, very tasks that require a lot of effort, right? Like a lot of to carry heavy robots or get the pressure, for instance, for grid blasting applications and things like that. So there's a big line of research of people working in this area. Right, so those are some of the highlights of, so only some. There is a limit of what we can, oh, sorry. Okay, so this is, now I'm gonna quickly talk about the highlight projects I'm working on. So I'm part of the Australian Robotics Centre. It's a ITTC, so Transformation Training Centre. And it's in collaboration with QUT and Swinburne University and a lot of partners too. What the aim of this center is to do cobots for advanced manufacturing. So the idea is to improve or upskill the manufacturing industry in Australia. And the project just started last year, so we're still recruiting and doing things, but we're started already projects with some of our partners. For instance, we're working with InfraBuild here in Sydney. So I'm just gonna stop this one. And okay, so this is a project. So we have a big collaboration with MLA, Meat and Livestock Australia. This has been for many, many years. My the other academic that is working on this one is Ellen Pujovic. And yeah, we've been working with UNE to work towards condition assessment of livestock and carcasses. And the idea is to get more objective measures of what they for yield of meat, right? So this is full meat industry, not dairy, and meat. Hopefully to make it more efficient, I guess. So the other work I have is well, I have an ARC discovery project that just started last year, where we are looking at robotics perception in unconventional sensing and unconventional sensing. Well, here I'm showing an event-based camera, but yeah, we're looking at magnetic sensors for like magnetometer, for instance, trying to do localization and mapping with this type of sensors, microphone arrays, things like that. There is a project that I actually collaborated with Diorella and Don. It hasn't started yet, but we've been talking for 2 years already. It's been a long process, but yeah, we're signing the contract probably this week. And it's a CRCP about a bionic visual spatial prosthesis for the blind, which means glasses for blind people. The idea is to bring perception to the blind. So we do the machine perception and communicate it to the user through sounds. This is just a collaboration with DLR in perception for planetary environments. This is a collaboration. We got a grant a few years ago to do traveling between DLR and my group, and we got another grant, so it's been like 4 years. Well, we will be like working with them with 4 years. Okay, so I'm gonna start, and these are some of our cool robots. We recently got a Spot, which we are super happy about, but we have another bunch of more less like looking robots and some other looking robots that are pretty useless too. Okay, so let's get into the technical talk. As I said, I'm gonna talk about 2 main topics. The first one is our recent work on the log Gaussian process implicit surfaces. So it's what I'm gonna present is a continuous and probabilistic Euclidean way to compute a Euclidean distance function and implicit surface for mapping and planning, right? So the idea is we have a depth sensor, some sort. It could be a camera, 3D camera, or a LiDAR. You move around and you build and you estimate the distance to the object and get the reconstruction of the surface as well. This is a work that we was published in RAL last year. So, and I apologize. I will have to throw equations here, and I have lots, but I try to make them, yeah, not so bad, let's say. So let's define what's distance. So, yeah, like the distance in the 3D Euclidean space can be captured by the Acknowledgement equation. The idea of, or the insight of the Acknowledgement equation is, imagine you have, consider an object, yeah, and the boundary of that object, which is what we call delta S, dilates along along is the normal direction of the surface, right? With a unit speed. So the arrival time, it's equal to the distance. Yeah, so that's the kind of the intuition captured by the Coulomb equation, which is this one. So, and this equation, for a lot, like especially the computer graphics community, has been trying to solve it for many years, but it's a nonlinear equation, right? But well, our aim is to recover this distance through sparse measurements and then reconstruct the surface, right? So now we have introduced a little bit of notation. We have S and X and the distance. All right, so we're going to use the Kernel equation because it elegantly describes the distance, right? But as I said, it's nonlinear, hard to solve. But yeah, but there are works around, and that's what we are leveraging now. So the guys from, again, computer graphics community, very good mathematicians, found that there is an approximation of the distance, of the solution of the distance, through what they call is Baradan distance. And it's through a screen Poisson equation like the one I'm showing here. So the intuition of this is, so now we have the object, yeah, and obviously the object is our manifold, which is S, our boundary is delta S, and the intuition of Baradan's distance or the heat kernel equation is that the distance propagates on the surface like heat, right? So if you pinch this bunny in some place, like you can see how the distance changes with in this wave form and then hits the boundary, right? So with this intuition, these guys found that there was a relationship between this, what they call this heat kernel, which is B, and the distance through the logarithmic of B. And that's our key thing for our log GPI. You can see where I'm going now. So, okay, so the approximation of the distance is the log of the heat kernel. And if we substitute B in the previous equation, we can show that the heat kernel, it's a regularized form of the Kernel equation. So that's very nice. So that's not our work. Somebody already did it. Crane in 2012. But okay, so our case, it's slightly different because we're interested in the distance outside the surface, right? Like in RD. So in our case, the boundary is also the complement. It's equal to the complement, and if we do this mathematical manipulation, we can see we can use it. We can use it for the rest of the space, but we lose the sign. So before it was sign, now it's not sign. Too bad, we lost the sign. But we can still get the distance to the object, and we can still get the boundary. So we thought that's pretty cool. All right, so implicit surfaces and what the Gaussian process implicit surfaces. So implicit surface, it's hopefully everybody who knows a bit of perception, it's familiar with. It's a typical TSDF that everybody has used once at least, probably, especially with GPUs. Yeah, so it's 0 on the surface, positive outside the surface, negative inside the surface, typically. Commonly the GPIS, which is the Gaussian process version of this implicit surface, models the distance as a GP, right? So I'm not gonna get into GP theory or anything. It's kind of an old tool, but as you can see, we've been using it a lot. So anyway, the GP, you can see it as the generalization of the Gaussian distribution for functions, right? So you model with this probabilistic function, the surface, the implicit surface, and you can model the distance, which is what many people have done with GPIS. So we came and decided, okay, so what should we, maybe we should be modeling the heat kernel as a Gaussian process, and then just take the logarithmic and get the actual Euclidean distance. And yeah, I mean, that's what we did, right? So we model the heat kernel as a Gaussian process, and then we get, just through the logarithmic, we get the distance to the surface. And that works very well. Anyway, there is another thing that Sarka, which is a guy who's been working with Gaussian processes for many, many years. He's like the Gaussian process and estimation guru. He already thought about heat kernels and Gaussian process, and he actually shows that the Whittle kernel satisfies the screen-Poisson equation, which is that regular form of the Kernel equation that we got through the heat kernel. That's great, because we can just use the Whittle kernel, and we know that model that satisfies the equations of the heat kernel. It's beautiful, but the only problem is in our implementation or in our setup of Gaussian processes, we also use the normals, and that's the derivative of the Gaussian process. And so we want to be able to differentiate our kernel, to be able to get the normals for free. And this kernel is not differentiable. But we showed that if we use a Matern 3, which the approximation to the Whittle kernel is not too bad. And then we can, we'll just and lose a little bit of accuracy, but with the advantage that we can differentiate the kernel once and we get normals for free. So that's what we did, and we get our mapping framework for with point clouds. In this case, purely mapping, so we get the poses and then the point cloud, and we can recover distance to the surface, continuous distance to the surface, because as a GP you can query outside your observations, and you get full continuous distance to the surface, and then through like finding the zero crossing, we can find the surface itself. For 2D, it's as simple as just going through the rays and finding the zero crossing. For 3D, there is an algorithm that it's called marching cubes that allows you to do the reconstruction. So then we have a representation that allows us to do visualization, and you can imagine distance and direction to the surface could help you navigation, right? That's my planning contribution. That's it. We didn't actually throw a planner with this representation. We did it with GPIS, and I think you probably saw it in a past seminar, like Liang presented some of the work that we did in planning for that, but without the log, unfortunately. So we can do 2D, 3D. We compare it with standard GPIS and BoxBlocks, which is another framework like ETH framework to do distance, Euclidean distance estimation, which they actually realized, okay, a great representation for planning and mapping is the Euclidean distance field, right? So in their paper, they actually show planning, not like us, but they already realized that the problem is they have TSDF and then they convert it to a ESDF. So it's not as neat or as elegant as a framework, and it's not probabilistic. So they cannot, and not a generative model, so they cannot fully recover areas that haven't been seen by the sensor. Anyway, our method is better. Better in mapping, not faster, right? So as you can imagine, yeah, they have a very optimized code that is way faster than ours. But ours is, despite using Gaussian process, which we all know it's a computationally expensive thing, we can do it online, okay, mapping only, right? Given the position, we can do online. I'm not saying real time, like it takes like 4 seconds or at least, but you can, the box blocks takes like, while we take 4 seconds, they will take 1.5. So it's, yes, we're worse, but better. Anyway, we are extending this. So that was published in RAL. We're extending this to combine it with odometry. So doing both odometry and mapping through our representation, and we're gonna submit it soon. So this is just a sneak peek of what we're doing after that. Okay. So how I'm going on time, I have no idea, but so, thank you. I have plenty of time, so I can tell you more things. So moving from the log GPIS, we have also a lot of work on using for continuous pre-integration for inertial systems. One of my PhD students did his thesis on that, and he expanded and expanded. We continue working on this topic. So, so why do we want to do pre-integration when IMUs? Well, I guess you're probably very familiar with. So we want to combining the inertial information with other stereosceptic sensor, or that gives us a lot of information. For instance, in vision, we can get scale and we can go faster because we can integrate measurements, get positions in a faster rate. We have been working on LiDAR inertial integration, which I will present later on, but it's also, it's the way we are using the inertial information helps us to undistort the point clouds. Even, typical, not the solid state, but the typical 3D LiDAR kind of rotate. If you're moving fast, your point cloud is all distorted and you have to undistort it. So the IMU is very helpful for these kind of things. But there are challenges, obviously. the multi-sensor, you need synchronization. The measurements come from at completely different times in completely different chunks. We have to also find the time shift between sensors that we have to intrinsically calibrate, and then we have issues with dynamic motions. So let's, sorry again, lots of equation. So let's have, and like Mitch can give us a full lecture on system dynamics for IMUs, but based on IMUs. But anyway, I'm not gonna go into that. Just to show these are the system dynamics where we have the rotation and velocities and position. So R, there's a rotation. Not gonna go too much into it, but yeah, we use all in manifold, so neat and nice. Velocities B and positions B, and we have our acceleration, our measurements from the IMU, which are F, we call F with a tilde, and the omega. Anyway, so just bear with me. You don't have to follow all these horrible equations, but you can see, like, you can integrate from acceleration to get velocity and then get position. And this is just equations showing that. In fact, work from here, they realize, well, okay, we have this integration that depends on the initial orientation, and that's a problem, because I'll show you now. Yeah, because I mean that initial orientation changes every time you if you're in a, let's call it an estimation system where you're recomputing every time your poses, that orientation changes every time and you have to reintegrate, and it's really annoying. So Luke Todd, who graduated from here with Salah a few years ago. I think Todd is still around, no? Did he come back? No? Okay. Anyway, yeah, they came up with this beautiful theory of preintegration, where you decouple the initial orientation from the actual measurements of the IMU and accelerometer. So essentially, you get these kind of pseudo observations called preintegrated measurement, and then that makes things simpler, and you don't have to reintegrate the whole thing. You can just use the measurements as it is. So it's a very neat framework. And then Foster extended. So back in those days, nobody was using orientated. They were using Euler angles, but then Foster came and they put it in manifold representation. So it all looks nice there. But anyway, it's Todd's actually idea. So we thought, why not we make it continuous? And we decided to make these pre-integrated measurements, which is the standard one, to fit Gaussian process to it and make them continuous. Why do we want them continuous? Because we want to be able to query at any point in time the measurement, or the pseudo measurement. We also, and that's the beauty of this work, we also can leverage the Gaussian process to help us integrate analytically. And that's the contribution of our work. So, all right, so this is our framework. So we have 3D gyroscope information, 3D accelerometer information, and then we do some things that I'll tell you now, but the idea is that we get these continuous rotations and continuous velocities and positions out of the measurements of the IMU. So let's go to this area where we integrate the accelerations projected to the time one. And remember, like, we are talking about, if you picture a factor graph, if you're familiar with it, but don't worry about the factor graph. So if you're estimating discrete time states for your system, you will have your poses at different time steps. What we are doing is getting this continuous information between these two states, right? So it's discrete in the estimation and then continuous in between. So we integrate from time 1 to time 2, from time 2 to time 3. So it's not long windows of integration or no. All right, so what do we do? So we, first, the F tilde it's our accelerometer information. We need to project it to time 1. Yeah, so we just need to rotate it to be in time 1. And then we fit a Gaussian, we model this as a Gaussian process. I think it's this. Yeah. So bear with me here. Bear with me with these things, with this L in MATCAL. That L is what we call linear operator, and it simply represents the integral. You'll see why we use it, why we call it this way, because for the once you do it with Gaussian processes, it's a very neat notation. But these are just simply, they are not matrix multiplications. It's the operator to a function, right? So in this case, the integral of the acceleration to velocity and the integral of the velocity to orientation. Sorry, to position. So again, as I said, if we do it with a Gaussian process, we can analytically integrate the kernel. If the kernel is you can integrate it and then get directly velocities and positions for free. And you can see here, this is just an example of the typical numerical integration that everybody does with the standard method, yeah, with the standard pre-integrated measurement. You get some error because of the numerical integration. While if you do it with the Gaussian process analytically integrated, you get a very nice fit. All right, so as accelerations is easy. Velocity is not so easy, right? Because you cannot integrate them just like that. In fact, you can integrate one axis, but once it's biased, that's it. That's useless. So you have to do something more complicated, right? So initially, in a first work that was published in RAL in 2001, we actually integrated analytically the accelerations, and then just simply fit a Gaussian process and integrate numerically for the rotations. But in the RSS paper, we found a way to do an optimization to get the analytical integration through optimization. So again, we fit a Gaussian process in the minimal representation of the rotation, and bear with me, that's R, right? Like if you're familiar with the theory of rotations on manifold, this is the axis angle rotation, that's the vector. That's like the derivative of that is what we fit as the Gaussian process. We can integrate it and get the rotation. So again, our linear operator here. But I mean, just to have the conditions that we need to satisfy to be on the manifold is that the right hand Jacobian, and I'm not gonna get into that, but like if you know about a little bit of the theory of the on the Lie algebra and the theory on the manifold, like it's a typical, this is the typical equation to go from angular velocities and express it in terms of the rotation and the derivative of the rotation. Yeah. So, and this is how you convert from rotation matrix to rotation vector. Okay, so, all right, so notice that these guys, and I go back here, these guys are not the measurement anymore as we had for the acceleration case. They are something that we call inducing values, and that's, we optimize, yeah, we get some residuals and we optimize these values, these inducing values for our Gaussian process that satisfy the constraint of the manifold. And we get the rotation, the rotation and the derivative of the rotation integrated analytically and inesotally. So believe me, you get better better estimates. obviously it comes with the computational time. Yes, there is no discussion. Having said that, it's still manageable because, as I said, it's just integration during, like, between keyframes, right? So you can still do that online. It is more expensive than what the standard PMs, like pre-integrated measurements, but usually, like, with small delta t is pretty reasonable. Okay, so how do we use that? So this goes into the third bit. And this is just no equations, or maybe one or two, but nothing. This is just how we use this unified Gaussian pre-integrated measurements. That's how we call them, in an LiDAR inertial framework. So we have something that we call into llama, which is inertial LiDAR localization, auto calibration, and mapping. So we started with calibration, then we moved to localization and mapping, and then it became the whole thing, right? Inertial localization, auto calibration, and mapping. Anyway, so as I mentioned before, like the LiDARs are not really like global shutter sensor, so we have to understand the motion. And what we can see there, as I'll show you later, is that the points of a LiDAR are our measurements, not the scan. Yeah, so we get rid of the scan concept and we just measure. All right, so this is what I'm saying. So we just put it in our very standard tools, a factor graph optimization, where we tightly integrate the LiDAR and the IMU. And we estimate pose, velocities, IMU biases, time shift, and extrinsic calibration, everything. This is not real time, far from it. But at the end, you get a good map, right? Like you go with your LiDAR and you get a map. Right, so we have LiDAR. The LiDAR factors are just simply point to plane and point to line constraints. And we have the pre-integrated, our pre-integrated measurements are used to correct for the position of all the points that we use in the LiDAR factor. So that's where it becomes very tightly integrated, right? Using the IMU to get the distortion of the point. And then we have the IMU factors, which are standard IMU factors. We get biases with posting and time shift. That's the standard method. All right, so so you can see in here, like we use the actual integral of the position and orientation to be able to project the LiDAR point into the LiDAR scan, which is what we are estimating. So we're estimating at the beginning of the LiDAR scan, our state is at the beginning of a LiDAR scan, right? So we still go at that frame rate. So we undistort the point cloud by using the pre-integrated measurements and projected into the LiDAR scan, the time at when the scan started. And that, that corrects for all distortions and then minimizes the point to plane and point to line distances. So this is kind of the factor graph. For people who are in estimation, this is a very standard thing where we use, we use the standard tools of SE3 and SIRIS for nonlinear optimization, where we have the factors of the point to line and point to plane, the intersensor shift constraints, and the IMU, the IMU biases, and the what's the red? The frame-to-frame constraints from the IMU. Our front end is very simple. It's similar to Loam, a bit better, but not much. Just yeah, optimized for getting nice points spread along the plane. So in Loam, most of the plane points are constrained, like in the center of the plane. Our features are slightly better. It allows to kind of have a spread, but very similar. And we also consider we don't have to do just a 360-degree scan. So we actually let it go and have more than 360-degree scan, and that helps the association as well, constrains it better, as you can see here. Okay, so nice results. This is our lab. Oh no, this is our office. My office is somewhere here. And then this was just, we have a LiDAR with an IMU, and Cedric walk around moving the LiDAR up and down. And yeah, that's the type of map we have. Yeah, this is not a super fair comparison. Loam runs real time or online. Ours takes hours, but it's trade-offs. And yeah, we can, obviously that's you can go outdoors, indoors, doesn't really matter. Recently we mapped a train, the super nice train of the Powerhouse Museum, the one in the entrance. We mapped it with this system. So yeah, it does get pretty good results. So last thing, and I'll probably just rush it. I mean, this is just to show we use it in LiDAR inertial system, but we also use it in a event-based camera LiDAR system. Why? Because events come really asynchronously, right? So it's the same problem. And if you can project them into a frame, then you can do this. The estimation much nicer. But events are very hard to deal with. They are super noisy, so they are more of a pain than anything else. But anyway, we'll still try it. And it's I don't know if you're familiar with event cameras, but it actually gives you a stream of data, not frames, but it's still captured by a CCD, right? So it's still you can still get position on an image, but in a continuous stream. And they give you XY coordinates, time, and polarity, which is whether the change was positive or negative, because it captured the change of intensity. So if you have an event camera in a static scene and you don't move it, there is nothing. It's when you start moving that you capture those changes in the intensity, especially in the borders of the objects, right? So in the edges. So yeah, the event cameras are pretty good in the sense that you can use them when there is very high, you can go very fast, right? Like it's very fast information that you get from the sensor. When there are low light conditions, they still trigger links. It's really useful for that. And by itself, just by moving, you get edges. So and that's the thing that we exploited in this work. And then the problem is obviously it's very asynchronous and has very little information as one event. You have to put them together to have more information. So similar to IntoLlama, factor graphs, and in a tight integration of inertial and events. Then we use 3D lines. So on this, I'm just gonna go fast, the same thing. But the difference is we use lines, and I'll show you here. So the events produce this 3D representation, which is the image and the evolution in time. So the space-time is a 3D thing. And if, let's say, for instance, this is a very well-known data set in events with the shape data set. So the camera just moved in front of this thing. So especially for this data set, it's just beautiful because you see in the time-space domain, you can cluster the events, and they by itself give you the representation, right? If you cluster the events as planes, I think it's hard to see here, but yeah, like we are getting planes, and then we project those planes and we get lines, and those are a representation. Anyway, I'll probably should finish. So we use that front-end type with the backend that I mentioned, and we get some decent results. We compare them with a vision-based visual odometry, so it's not very fair because the vision is much better, but we show that they actually work pretty decent, at least in these simple cases. All right, so acknowledgement, my LAM, my PhD student who is finishing, and it's is working on the GPI in the Gaussian log GPIF, and Cedric, who is the guy who's been doing the inertial integration. And then lots of collaborations, including Lian, that was part of the GPIS framework, and then people from ETH that we work for the events camera. So yeah, just conclusions. Yeah, we'll present a representation for surface reconstruction and navigation. We can get direct computation and continuous computation of the Euclidean distance field. And then we have continuous pre-integrated measurements that we can use with any asynchronous sensor. So far, we will see. Keep trying other applications. And that's it for me. Thanks, guys.
Thanks, Teresa. Fantastic. I think Into Llama is probably the best acronym I've seen.
I love it. And did you see the? Wait, I have to show you because I was gonna. So that's the logo.
Yeah, I can see. Any questions for Teresa? So I'm just monitoring the
Yeah.
online chat.
Oh, yeah. Yeah, thanks, Teresa. That was great. With the implicit surfaces, so it's, I guess I haven't looked too much into depth in that area, but from what I understand, it's often used to kind of, you know, where the zero set is, that describes the shape of some object.
Mm-hmm.
But you're getting the whole distance field. And you mentioned navigation. It seems like there's a strong possible connection there with optimization, the way barrier functions are used for, you know, you've got constraint sets that go to zero in regions you can't leave. So people often use like logarithmic barrier functions on that. You know, basically, when something goes to zero, that's bad, right? So you have
like potential fields or things
like a potential, yeah, kind of the opposite of a
yeah,
right?
Yeah.
It goes to infinity as you approach the boundary,
Yeah,
right?
yeah.
And then you can use that. What's pretty common in control these days is you use that as part of a control the outcome function or something to, you know, to guide the motion of something to stay within a bounded region, right? So this seems like a very natural.
I know, and I thought, yes, I mean, we should probably have a further talk on this because I've been talking to my students saying like there must be some nice planner that leverages this representation in a very neat, sound way. And we haven't found it, so I think I found my man. Yes, awesome, thanks.
Got a question from Don online.
Oh, yes.
No, Don, if you.
Don, you have to.
Speaker on.
My Zoom is low.
Yeah, hi Teresa, can you hear me?
Oh, the speaker is not on. Wait.
Can you hear me?
This is a problem. Can you put it on?
It's gonna.
That's gonna mess up the whole thing.
Wait, let me try it.
Okay, I put it on. Okay, so and hopefully.
Hello.
All right, done. We can.
Hello.
Yes.
You can hear me?
Yes.
Excellent. Thank you, Teresa, for that talk. Really stimulating, great stuff. In the first half, you were talking about implicit representations. I get really excited about these, but mostly I think about implicit representations for visual appearance. And you're talking about implicit representations for physical stuff, for the geometry. So my question is, what's your opinion on putting those together? Somehow represent both at the same time? Is there any future for that in robotics? Are there any?
The objects and what else, Don? I think I missed that.
Yeah, so visual appearance. If you look at Nerf, for example.
Yes, yeah. All right, so that's probably the next PhD student. yeah. That would be like epic just to put both together. Minimizing the photometric error together with the distance field. I think that will constrain beautifully.
So you reckon there might be some new representation at the intersection of these things?
Yeah, well, maybe. Will be cool to look into. Yeah.
Yeah, cool. Thanks. Let's maybe chat about that some more.
Yeah, sounds good.
Awesome.
Any other questions for Teresa? Yes, Fiorella.
Congratulations for the great talk. Amazing work. So I'm a bit puzzled about VIOs and the sensitivity to everything that you put in there. So the synchronization and especially the distance calibration, from your experience, is this solved? So I see.
I like to do it as a joint optimization. Is that the question?
So the question is, you have one work that it's not calibrating on the fly, and the second one is calibrating on the fly. Was that the problem that we have to have?
No, the calibration on the fly was just because we could.
Okay.
So we actually formulated the first work of Into Llama before it was called Into Llama was just LiDAR inertial calibration through the exactly same tight integration of points and IMU measurements. And yeah, that worked very well. So we thought, okay, we can now do localization and mapping. And then we thought, okay, so we already did two separate things. We'll just put it all together. Having said that, practically, I think there must be something not really completely observable because, and that's something that needs to be looked further. So we do the full Into Llama, then once we believe the calibration, like it's just heuristics. Once the calibration is done, it's locked, and then we continue doing mapping. I think if you let it free, eventually diverges because it can find other solutions.
But I'm also, so what I noticed is that we take a VIO from GitHub and you run it on a new rig that you calibrate with whatever calibration tool, and it's completely failure. So from my experience, those VIOs, they run very well on the data set that are provided, but then you have a new rig.
In the yeah.
And so they are sensitive to the calibration.
Yeah, well, we use Rovio and it does calibration on the fly. And those, I mean, the problem is they have so many parameters that it's just hard. You don't know what is not working, your ability to tune parameters or the system itself. But it works in some scenarios with auto calibration. I think it depends on the system, how it's done.
I think it would be interesting to look into how sensitive
yeah. That there are there are more theoretical things I reckon to look into.
And another just curiosity, how this implicit representation extends to large scales as you're looking.
So the implementation that we have, it's not, we didn't build it from scratch, so it comes from Bottom's thesis, which was in I think she was in UPenn, like now she moved from there, but she had this beautiful like online Gaussian Process Implicit Surface mapping, and we build from it. And it uses kind of clustering, so it's kind of sub-mapping kind of approach. So that's what it allows you to go to map big areas because you don't propagate back. Having said that, in the framework that we are developing for odometry and mapping, we use the implicit surface for association, and that's where it becomes very time consuming. So the bigger the map, it becomes very computationally expensive, despite it's still clustered, but for the association, you have to consider bigger maps, right? Like bigger areas, otherwise you don't constrain it properly because it's all based on curvature. If it's a flat wall there, you associate with the flat wall, but you don't know where you are. I mean, it's the same problem as with LiDAR or camera.
How the nerve would say it here?
The what?
The nerve.
Nerve?
The neural representation.
Ah, the nerve. Yeah, the neural. Yeah. Something to look into the future.
Any other questions for Teresa? Okay, great. Thanks a lot,
I
Teresa.
think there was one last question. Somebody last minute one.
Ali, is that you got back with it? No.
No, it was.
Sorry, I missed.
So in your talk here, there's a pre-integration of the signals and quite similar to calculating the system state transition matrix in control theory, and we use it as a parameter estimation based on observer. So it provides a way to transform the state estimation formula to the estimation of parameter, and we need to calculate the state transition matrix. This is quite has a very strong connection.
Yeah, and look, this idea, I think that the integration, well, I mean, modeling with a Gaussian process, which you can see I am a little bit fan, that it allows you to have a generative model, right? So you can also use it like for a prediction kind of thing. I don't know, like if that, yeah, like for model predictive control or something like that. Might be something I like it. Yeah, I'm not the control planning kind of person, but I reckon there is something that can be leveraged in that area.
Okay, thanks very much for that. It actually carries on from the question that he asked. Just to enhance my understanding, you skip the transition matrix to compute like a matrix exponential. Essentially, what you're doing is you're replacing a matrix exponential with a Gaussian process. Is that basically what's happening? Instead of doing like a numerical approximation.
Yeah, that's correct. That's correct. So you're generating a model. I don't know if you can use it just straight away as a state transition matrix, right? Like that's a question for you guys. But but yeah, essentially you have a function, right, of some sort. It doesn't matter that it's a data, like it's an implicit function, but you have a function, so you can use it in the same way that you use real functions.
I just had a quick question, I guess, following up from that.
Yeah.
How does it, so you're comparing that, I guess, with a first order integration scheme.
Yes.
How does that compare then with higher order integration?
Yeah, so we did the linear one as well. It's still better. I guess if you fit more and more orders, I guess it will eventually catch up. Depends on the motion. So what we've seen is that in a very dynamic motion, all these integrators are not the best. I mean, they always struggle, and the faster you move, and you have to impose the model. That's the other thing. So my student keeps saying, well, it's not my student anymore, it's postdoctoral, but he keeps saying that like our approach is model free, right? So kind of model free. You have a kernel, right?
Yeah.
And a very small kernel that you can do all the cool things. But
Okay, well, let's thank Teresa again. Thanks for the